We're beginning chapter 2 now, the chemistry of life. Sometimes you'll hear me refer to this as biochemistry because what we'll be talking about is really just chemistry that's related to living environment. If you were to take chemistry as a course, you would get into much more detail than we get into this chapter. The first section in this chapter is titled The Nature of Matter, and it basically discusses atoms, elements, and chemical bonding. Our key concepts that we're looking at are what three subatomic particles make up atoms, what are isotopes, and what are the two main types of chemical bonds. So living things consists of atoms of different elements. The atom is the smallest basic unit of matter. And an element is one type of atom. So an atom is the smallest basic unit of any piece of matter, and an element is a group of that just single type of atom. So you could be holding a chunk of carbon in your hand, and that is considered the element carbon. It's made up of millions and millions of atoms of carbon. Here we have a hydrogen atom and an oxygen atom. If you notice at the end of those titles, there is a letter in parentheses, and that represents an abbreviation for that particular element. Many of the elements have a letter that they begin with, the first letter. Some of them have slightly different abbreviations. Please make sure you highlight vocabulary terms as you go through these notes. An atom has a nucleus and electrons. So the nucleus is found in the center, and the electrons are found around the nucleus in different energy levels. The nucleus will be made up of protons and neutrons. Protons are positively charged particles. Neutrons are neutral. And hopefully you can remember proton and positive both start with P, and neutron and neutral both begin the same way. And electrons are found in energy levels outside the nucleus. Electrons are going to be negatively charged. So in atoms that are in a normal state will have a neutral charge because the number of protons typically equals the number of electrons. So the positive and negative charges cancel each other out, and that atom will be neutral. Here's a diagram of an oxygen atom. At the very center, you find the nucleus, and like we said, the nucleus is made up of protons and neutrons. Now, around the outside, you'll find 8 total electrons, and it equals the 8 protons in the nucleus. However, the electrons are found in different energy levels. The two that are closest to the nucleus are, you usually will just find 2 at that innermost energy level, and then whatever is left falls into other energy levels outside. Now, oxygen's a pretty small atom, so it only has a few energy levels. There are some atoms that are rather large, and they will have multiple energy levels. The key here is that all the levels, except for that first one, prefer to have 8 electrons in them. And here you can see there are 6 in the outermost energy level. This is going to be the key to bonding between atoms, because if they want to have 8, they need to either steal electrons or borrow or share them or give them away to other atoms. And we're going to talk about how that happens here in a few slides. Make sure you highlight again. A compound is made of atoms of different elements bonded together. For example, water. Water is made of 2 hydrogen atoms and 1 oxygen atom. Atoms joined together by covalent bonds form molecules, and these are the smallest units of most compounds. So here's the molecule of water. 1 bigger oxygen atom, and then hydrogen atoms are rather tiny compared, so they kind of stick on the sides there. Some more highlighting. Here's a diagram of carbon dioxide, another type of molecule. It's made of one carbon atom, you can see it in blue in the center, and two oxygen atoms, which are located on either side. Many other carbon-based compounds are found in living things. Carbon dioxide is definitely one of them. We will talk in a couple sections about these specific carbon-based compounds. Carbon is unique because it has those 2 electrons in the inner energy level, and then it has 4 in the outside energy level. And remember when I said most of these atoms want to have 8 in their outer energy level. So that means carbon can bond with up to 4 other atoms. And this is a very unique thing, and that's why carbon works so well for living things. If you take a look, carbon and oxygen, these 2 oxygen atoms, are sharing electrons. So the carbon feels like it has 8 electrons, and you can see right here, I'll count them with you, 1, 2, 3, 4, 5, 6, 7, and 8. So it feels like it has 8 because it's sharing with the oxygen. And if you count around the oxygen atoms, you can see that they feel like they have 8 as well. And this is called a covalent bond. This is a really strong type of bond. They don't really easily break. It takes a lot of energy to break these types of bonds. A covalent bond forms when atoms share electrons. Carbon especially can have multiple covalent bonds. Sometimes you'll see diatomic molecules, for example, oxygen likes to pair up with another oxygen atom. The air that we breathe, the oxygen that we take in, exists as an O2 molecule. That's a diatomic molecule. Then here's our diagram of carbon dioxide again, showing us the covalent bonds and where they are. An ion is an atom that has gained or lost 1 or more electrons. So sometimes the electrons get ripped away from an atom, or they steal an electron from another atom. And when that happens, if you remember, electrons are negatively charged. So that makes the entire atom either more negative or more positive. And when it becomes charged like that, we call it an ion. So we see positive ions and negative ions. And then because there are charged particles, we know opposites attract, and this is going to form something called an ionic bond. So a good example is table salt here. It's made up of a sodium atom and a chlorine atom. And if you look, sodium has one lonely little electron right here in its outer energy level. And if you were to count, chlorine has 7 in its outer energy level. For these 2 atoms, it's easier for sodium to just completely get rid of that one little electron, because then if you count, the next energy level down will have 8. This causes it to lose a negative charge, which means it becomes positively charged, and you can see that on the right side of the diagram. The chlorine, because it has 7 in the outside, would rather just steal 1, and it takes it from sodium. And now the outer energy level in chlorine has 8 electrons. And because now chlorine it gained a negative charge, it's more negatively charged, and sodium is positively charged, they attract each other. And this is what they call an ionic bond. So they're not sharing electrons, they totally donate 1 and gain 1. This is another type of strong bond between atoms because of the charges. This is a square out of a periodic table. In chemistry, you'll meet many more atoms and elements. Here we're just showing carbon. There's a lot of numbers and symbols on the periodic table, and this is just what a few of these mean. So in the middle you can see a C, and the C represents carbon. Not all periodic tables will actually write the name of the element, so sometimes you have to memorize what all the symbols stand for. At the top is a number 6, and that represents the atomic number, and the elements are arranged by this atomic number. They get this atomic number from the number of protons. So carbon, any carbon atom that you find will always have 6 protons. That is how it is identified. That's its identification, you could say. And then at the bottom there is a 12.011. That's the atomic mass. That's how much mass carbon has. The mass is made up of the protons and neutrons. Electrons are so small that they really don't have much mass. So the mass that they talk about is basically just coming from protons and neutrons. Now you can see it's 12.011, and we know there are 6 protons in the nucleus, and if you subtract the atomic mass from the atomic, or subtract the atomic number from the atomic mass, you get 6.011. That's approximately 6 neutrons in the nucleus. And then you can kind of figure out by process of elimination that way and subtraction how many neutrons. Not all elements will have the same number of protons and neutrons. Sometimes they have a lot more neutrons in their nucleus. Then we have something called isotopes. These diagrams are showing you isotopes of carbon. Atoms of the same element that have different neutrons are called isotopes. Isotopes are important when we talk about radioactivity, and if you look all the way to the right is an atom of radioactive carbon, and they call it carbon-14. This is the element that they use for radioactive dating for fossils and rocks and things, because when there's extra neutrons, as you can see, there's 8 neutrons in radioactive carbon-14, there's a certain element of breakdown of that nucleus to get back to normal. And scientists have been able to measure and calculate that it's a very regular breakdown. It happens at a consistent rate. So they can figure out how much of this radioactive stuff is left in a fossil, and then that's how they know how old that particular fossil is. Okay, so you will be taking a quiz on section 1 now. Also, there are videos in chapter 2. There's also an activity I want you to check out. So good luck on the quiz.